This is the screencast for section 2.4, example 6. We're going to look at instantaneous speed and instantaneous rate of change. Now you learned all about that in section 2.1, so this isn't really new, but we are going to go back to your train of thought. Woo! In section 2.1, that's not the sound that going back in time makes, but I can't make that, so that's fine. We're going to go back to 2.1 example 1, and we were working on the average speed of this rock falling off of a cliff, and we were looking at its position at time 0 and time 2 seconds, and we found the average speed or slope. We also did the same for 0 seconds and 3 seconds. So now we're going to find the instantaneous rate of change of that same rock. The formula for vertical free fall, where your input is time and your output is feet, is f of t equals 16t squared. So we want to know the instantaneous rate of change, or the instantaneous speed at 1 second. So the 2 points I'm going to use are 1 comma 16 and 1 and a tiny little bit comma 16 of 1 and a little bit squared. So again, I set up my difference quotient, multiply everything out, simplify, cancel, blah blah blah, plug in 0 as a result of taking the limit, and I get 32 feet per second. So if we go back to example 2.1, we found that the average rate of change between seconds 0 and 2 was 32 feet per second, and now we're saying that at exactly 1 second, its slope was 32 feet per second. It was instantaneously at 32 feet per second. Now, after 1 second, it was greater than that, and before it was less than that because its average was 32. But at the instant, 1 second, it hit 32 feet per second. Coincidence? Oh, I don't know. The now try problem number 27 says the equation for free fall at the surface of Mars is s equals 1.86 t squared meters with t in seconds. Assume a rock is dropped from the top of a 20-meter cliff. So again, its initial velocity is going to be 0. Initial position, we're calling the top of the cliff position 0. Find the speed of the rock at t equals 1. So my 2 points are 1 comma 1.86 and 1 and a little bit comma s of 1 and a little bit. So I plug those into my difference quotient, take the limit as h approaches 0, and I get 3.72 meters per second, which means that the speed of the rock at exactly t equals 1 second is 3.72 meters per second. That's how fast it's falling. Now the rock only fell 1.86 meters, but it was falling at a rate of 3.72 meters per second. So that speed is really picking up there in that first second.